Good morning, everybody. Okay, so in the previous class, we started the IIR filter design. Any questions? Okay. And we said we're going to look at 3 different techniques of IIR filter design. The first technique was the pole zero placement method. We place poles and zeros to achieve a certain frequency response. And the second method, we're going to design a continuous time filter, and then we're going to transfer it to a discrete time filter. And the third method is using a direct design using a minimization technique in order to achieve any frequency response that we desire. So in the pole placement technique, we said if we place a 0 on the unit circle, then at that frequency, the response is going to equal to a 0. If we place a pole very close to the unit circle, then at these frequencies that are very close to the pole, the frequency response is going to be very high. And therefore, by placing the poles and zeros, we can control the shape of the frequency response. Okay, so then we said we can, if we looked at the frequency responses that we generated using the pole zero, some of them looked very sharp, and we said we can flatten the frequency response and to do that, we can place multiple poles and zeros. And as an example, if we have that's you. If we place multiple zeros, something like this, and multiple poles, then the result of doing this is we're going to get a flatter response. So if I look at the frequency response of this filter, it might look something like this. Together? And the exact shape, of course, will depend on where we place these poles and the zeros and the number of them. But the fact that we have multiple zeros here, it means this low frequency all is going to have a zero frequency response. And similarly, very high frequencies, they're all going to have a zero frequency response. So this is going to be flattened, this is flattened, and to flatten the passband, we can also place multiple poles. Together? Okay. If we want to achieve a sharper response, how do we achieve a sharper response? We have to define what we mean by a sharper response. And we will see what that means in a second. But nevertheless, we have to place a pole near the 0. And we'll do an example later on with MATLAB to show that. So if I'm trying to remove a certain frequency, and I really want only that frequency to be removed, I want the frequency response to be passed. I don't want to remove anything other than that single frequency. What can I do? I have a frequency, omega 1, that I want to remove from the input of the filter. What do I have to do?
Do you place multiple poles?
Uh,
or just one?
to remove, in order to remove, what do I need, a pole or a zero? If I remove this frequency, a zero. It's 50-50. A zero. No?
Well, you said those X's up top were
Poles.
poles, right?
Yeah. I'm trying to remove, not to pass. These X's made it a pass time.
Okay.
A zero, remove it.
Oh, okay, right.
A zero on the unit circle means the frequency response at that location, at that frequency is a zero. Make sense, everybody?
Yeah.
So what do we need to do? We're going to place a zero on the unit circle. What does a circle mean? A zero, X, a pole. Okay, so if I place a zero here, I'm going to get a zero at these frequencies, but what I'm trying to do, I want to have a very sharp response. And therefore, what I'm going to do, I'm going to place a pole that is very close to that circle. What is the impact of placing that pole next to the circle, to the zero? The response is going to be sharper. What does that mean? It means the impact of this zero is going to be felt over a very small region. Does that make sense?
Yeah.
So if I'm at this location, there's a zero, there's a pole, they're almost the same distance, so they're not impacting me. Only when I am at this frequency, it's a zero, and therefore I'm going to be gone, I'm going to be removed. If I am away from that zero, I'm very close to both of them, and their impact is going to cancel each other. Remember, a pole and a zero, very close to each other, their impact is going to be canceled. So therefore, if I look at the frequency response, the frequency response is going to look something like this. Is that clear? So rather than if I did not have these poles, I'm going to have a frequency response that might look something like this. I can make it sharper by placing the pole very close to that circle. And the closer I place it to it, the sharper it's going to be. Together? What do we call this filter?
Notch.
Excellent. Notch filter. So if I have a signal that, for instance, I recorded of a sensor in this room, I might pick up the frequency that's coming from the electricity. I might get a 60 hertz on top of that signal that I picked. If I want to remove that 60 hertz, what do I have to do? I can do a notch filter. It will just remove that frequency from my signal. And again, we'll do an example, an example with some values that will illustrate this. Now, if we can do a notch filter, why can't we do a comb filter? What is a comb filter will do? As the name implies, or does not imply, instead of having a notch filter that remove a single frequency, I can repeat them and remove multiple frequencies. So what I can do, I can add a zero here, 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 zero here, zero here, and add a pole here, a pole, a pole, a pole, pole, a pole, and a pole.
One more.
Not going to do it. What is the frequency response of this filter going to look like?
bunch of fingers.
And that will look like,
Oh.
thank you. So if I look at the frequency response of this filter, it's going to look something like this.
It's more like fingers to me.
It's not done yet. Now you made it worse.
Sorry.
Even worse. Okay, so it looks like a comb. If you don't see it, nothing I can do. Negative pi to a pi. So what is this filter going to do? Going to remove this frequency, this frequency, this frequency, this frequency, etc. Okay. So this comb filter is like a notch filter that repeats periodically. And we can use it to remove interference with fundamental frequency that is equal to omega 1. Assuming this is omega 1. Together? So what happens, we might have a signal that is interfering, but not only that signal is interfering, it's interfering and its harmonics are interfering. Make sense? So I might have a system where I see a 60 hertz, 120 hertz, 180 hertz, all of them are interfering with my signal. So therefore I need to remove that interfering signal along with all its harmonics. And therefore I can design a comb filter that will remove them all. Okay. Now for this filter, for this comb filter, we have N zeros on the unit circle at frequency at omega equal to 2 pi multiplied by k divided by n, where k is equal to 0 all the way to n minus 1. And therefore, the fundamental discrete frequency that it removes is omega 1 equal to 2 pi divided by n. And the n zeros that we placed almost cancel with the n poles that are adjacent to them. Make sense, everybody? Okay. What is the transfer function for this comb filter? H of z is going to equal to z to the power n minus 1 divided by z to the power n minus alpha to the power n. This is going to give me n roots that are on the unit circle and n roots that are going to have a magnitude that is equal to alpha. Okay. And if you want to design the filter, we select our sampling frequency, or based on the sampling frequency. Frequency and the frequency to be removed. And let's call that F1, the fundamental frequency that we want to remove. We select N such that 2 pi multiplied by F1 divided by Fs is equal to 2 pi divided by N. Does that make sense?
What's FS here?
Which one?
FS.
Sampling frequency. So if I have a continuous time signal that I want to remove F1 from, a fundamental frequency that I want to remove, then what is that corresponds to omega? 2 pi multiplied by F1 over Fs. That omega will be 2 pi divided by N, which is the omega 1 that we have. Together? Everybody? Where is this coming from? Omega is equal to W multiplied by T. Okay, so then we can select our alpha, and then we can determine H of Z. Okay, let's look at a MATLAB example.
So alpha is the magnitude, you said?
Alpha is the magnitude of the pole. This distance is alpha. Okay. So here is an example where we have a signal at the input that is interfering, that has a frequency that is 100 hertz. And the sampling frequency is 1200. Together? So therefore, I have a 12th order filter. The filter order n is going to equal to 12. Therefore, what is h of z going to look like? Z to the 12 minus 1 divided by z to the 12 minus alpha to the n. Together? So therefore, I have the numerator of h of z, which is going to be all these zeros. Everybody knows how to represent polynomial in MATLAB? Yes? So this means z to the 12 plus 0, z to the 11, 0 to the 10, 0 to the 9, etc., all the way to the last element. Okay. So let's run this code. And what do we see?
Poles and then zeros.
We see the poles and zeros. of h of z, and these are on the unit circle. And then we see the frequency response of the filter. And what does it look like? A comb. And then we see the frequency, we see the response of the filter when we input to it a signal that has, what was the frequency we designed it for? 100 hertz. Together? All zeros, the frequency response. And we have, what is the last graph is we have the input signal, the 100 hertz sinusoidal signal, and this is the output of the filter. What did the filter do?
Low pass.
What did it do?
Filtered out
It removed that frequency. Does that make sense?
Yeah.
Everybody? Okay. Any questions?
You're going to put the MATLAB code there too? Or?
Yes, I'm going to do that.
Can you go back to the code? I just want to look at the code. So where is alpha defined here?
Very good question.
It's in B.
Very good question. So let me talk about how we calculate the output of this filter. So in order to calculate an output of a system, what are the three different methods that we can use to calculate the output of a system, a discrete time system? Yes, we can. If we have the difference equation, we can iterate and calculate the output. What is the second method? The third method.
Z.
Tell me the third method while you're thinking of the second method. We can do the impulse response and then do convolution. Make sense? Or we can use the command in MATLAB that is called filter. So what does this filter do? The filter takes the numerator, denominator of the filter, and you give it the input. And then it will calculate the output for you. Does that make sense, everybody? So if I do a help on the filter, so the filter, this is the difference equation that implements. So therefore, I have a transfer function that is A over B. Does that make sense? So this is multiplying across and calculating dy. B and A, these are the vectors that we pass that defines the filter, and we pass an input, and then it will calculate the output for us.
So 0.9 is alpha.
0.9 is the denominator.
But that's alpha, right?
Oh, that's alpha, yes. Yes.
Negative.
Is it negative? Because it's
It's a little
minus, right?
Yeah, minus. It is minus alpha to the power of n. Is that clear? Makes sense? So therefore, I have the B, the A, and then the filter. I can use the filter command to get the frequency response or to get the output of the filter. Sorry, I can, once I have the A and B, I can use the filter command to calculate the output, and I can use the frig to get the frequency response of that filter. Together? So the frig, I have to pass to it the numerator and denominator, and then it will give me the frequency and the amplitude, and then I can plot it. Is that clear?
Yeah.
Okay. Now what's not clear is the following. When the frequency that is returned to me by the frequency, I multiplied it by 1200 over 2 pi. Why did I do that? To convert it to hertz. So if I look at my frequency response that is generated, I have the frequency here in hertz. Does that make sense? So what is this frequency? The 1200? The sampling frequency. So I multiply it by the sampling frequency over 2 pi. It will give me the frequency. Otherwise, it gives me normalized frequency. So in order to unnormalize it, I multiply by the sampling frequency over 2 pi, and then I get my graph here. Now, somebody might be curious, like, oh, what's going to happen if we have, instead of 0.8, 0.6? Well, we can run it and see what happens. What happened? It's not as sharp. Does that make sense?
But it seems like it attenuated faster.
Well, the frequency might be faster, yes. Although, I mean, you have to really look closely to see, the transient response of it. Similarly, we can make it even bigger. How big can we make it? 9.9. Still responding. Where is the graph of the frequency response? It looks weird. Let's not go 0.99. Let's go 0.975.
So is that just numerical?
It looks like, yes. I mean, probably have to look closely at it. So you see, these, if you compare these to the shape of the one that originally had, what does it look like?
Sharper.
Sharper. What does it mean by sharper? I mean, these teeth are closer to each other. Okay. So, but since we talked about the 0.99, which is, let's make a point here. So when I do this filter, and I need to implement it, how can I choose this value? Like, why would I not choose 0.99? Or can I choose 0.99?
Close?
It's too close. I mean, it depends on the device you're implementing this on. If there's any rounding and it's going to round the 0.99 to a 1, then I'm not having a filter because the 1 and the 1 are going to cancel each other. Does that make sense? So how close and how many digits your microprocessor or controller that you're implementing it and how it's going to round these numbers, and hopefully we'll look at this at a certain point, will determine the resolution that you can have when you are having the coefficients for your filter. Make sense? Okay. But since this is just MATLAB, I mean, we can put any value that we like. Okay. Let's do another example. Actually, before we do that example, let me ask you a question, which is, if I have a filter like this filter is going to remove the DC, like any constant, because this is omega 0, is going to remove all these frequencies. What if I don't want it to remove this frequency?
Take away the
Pole zero?
Excellent. I can take away the pole and the 0 that are here. Make sense? How do I take them away?
Start in a different spot.
What else? Anybody else? Other ideas? Okay. Keep talking till I plot it. So what we're saying is this filter that we just did removed all these frequencies, which is great. But then imagine a situation where you really don't want to remove a certain frequency, which is this DC frequency, this omega equal to 0. I want to keep it. I don't want to remove that component of the signal. And the answer, you answered correctly. You said, just remove that 0. What is the easiest way to remove this 0? Very good. Correct answer. And how do we do that? We can just multiply by z minus alpha divided by z minus 1. Make sense? If I multiply it by z minus 1, then the z minus 1 that was the 0 in here is going to be gone. Z minus alpha, the pole that was here, is going to be gone. Is that clear? Everybody? Anybody understood this? Don't be shy. Not really? Okay. So what we're saying, everybody understood the cone filter and how it works. What we said is, what if I want to remove these, this pole and this 0? I want the filter to be such that it removes all these harmonics, but keep the DC. When omega 0, I don't want to filter anything. And we said, if I want to remove these, this corresponds to z minus 1. That's why I have a 0 here. I have a z minus 1 factor here. If I divide by z minus 1, the z minus 1 and z minus 1 here are going to cancel. So I'm not going to have a 0 at 0. Similarly, if I want to remove this pole here, this corresponds to z minus alpha. If I multiply by z minus alpha with z minus alpha here is going to cancel. And therefore, I'm not going to have a pole at alpha. Together? Is that more clear? Ask if it's not. Don't give me this look. Ask or tell me it's clear. Yes, no?
So if you go back to the MATLAB difference equations, what would that look like?
If I go back to the MATLAB, I'm going to multiply these, and that will be the difference equation.
Okay. So, but
I don't have the difference equation in MATLAB.
yeah, the numerator, the denominator. Okay, yeah, right. Okay.
But if I want to calculate the difference equation, so whatever this multiplication is going to be, whatever numerator z to the n plus 1 minus z minus alpha z to the n plus alpha. Make sense? Of course, this is, in reality, these will cancel a factor in here, and this will cancel a factor for here. So this is not going to be zn plus 1. Rather, this is going to be z to the n minus 1. Make sense? Because they're canceling each other. Okay, if it's not clear, we'll have a homework assignment that will do this.
You didn't paste the MATLAB code into the OneNote. Thank you.
Gwen, you're going to be in charge of reminding me of the MATLAB code.
How am I going to run it?
I mean, the easiest way to not only understand this, but to understand everything we're doing is to use MATLAB. Okay, I'm going to put it on the side, but you can, I think, still copy it as is here. Okay, let's do another example. And in this example, we're going to design a simple band stop filter to remove a 60 hertz noise or interference with DC gain that is equal to 5, and we are given that the sampling frequency is equal to 1200 hertz. What do we have to do? We can do a notch. However, we'll do a notch later, but we're going to do just a band stop without a notch. What is the first step to designing the filter? I want to see where I have to place my zero. Does that make sense? Where is my zero? Where do I have to place my zero?
Will it be, have a magnitude of 5?
What else? How do I find the discrete frequency that corresponds to the continuous frequency I'm trying to remove? We're going to convert it to an omega, yes. So W, the frequency, the continuous time frequency, is 2 pi multiplied by 60 hertz, and this is in radian per second. What I want to find is omega 1. What is omega equal to?
W1 times period.
W multiplied by T. And what is that going to equal to? 2 pi 60. And what is T?
Divided by 1200 hertz.
Is that clear?
Yeah.
I mean, this should be like very clear. We have a continuous frequency. I'm sampling it every 1 over 1200 seconds. Therefore, after I sample it, I'm going to have a discrete sinusoidal signal that has a frequency omega 1 that is equal omega t, which is pi over 10. That's how the filter, the discrete time filter, my digital filter, is going to be seeing this signal. Okay, so where do I have to place the zero?
Pi over 10.
Pi over 10. So at this frequency, this omega 1, which is a pi over 10, I'm going to place a 0. And I'm going to place another 0. Together? And then I'm going to place a pole at this location here. This distance is A. Agreement?
Why would you do that instead of 2 poles?
We'll do another example of that where we have 2 poles. Just to illustrate the frequency response, and because we're asked to do a band stop filter, not a notch filter. So we placed one pole. We'll do a notch filter with two poles.
With the band stop, you would need some type of value, I would assume, around the 60 hertz, right? Like, rather than like it just being a notch, like you want to stop some epsilon around 60 hertz, right?
I mean, what this filter is going to do is going to remove the 60, 100%, and around it is going to be attenuated. Make sense?
Yep.
Now, depending on like what I have at the input, maybe I just have an interfering signal and nothing around it. Therefore, I'm not concerned about what happens here and here, and therefore this might work. Does that make sense?
Sure.
So really, the exact shape will depend. Is it just an interfering signal, and around that band, I'm not really, there's no good signal that I'm trying to keep, and therefore, if there is a little attenuation, it doesn't matter to me. I can do it. If no, I just want to remove this one, and I don't want to impact any other because the signal has some components here that I want to keep, then I will use a notch filter because it's going to be very sharper. Okay. So what is the frequency response of this filter?
Let everything pass except some.
Sorry, did I say what the frequency response? I meant to ask what is h of z for this filter? So it's going to be z minus 1 e to j pi over 10 multiplied by z minus e to negative j pi over 10 divided by z minus a. Agreement? What is this equal to? This is going to equal to z squared minus 1.902113 multiplied by z plus 1 divided by z minus a. This is going to equal to 2 multiplied by cosine pi over 10, which is going to be 1.902. Okay. How do we find the value of a? The gain. I mean, since we have a gain specified, then that will, we only have one parameter to choose, and that is it. What is the DC gain?
5.
And what does that correspond to?
We've covered it.
The gain of the filter when omega is equal to 0. Together, that's why it's DC, omega equal to a 0. When omega is equal to 0, what is z equal to?
The distance from the zeros?
1. The z is equal to a 1. So this corresponds to h of 1. Is that clear? Make sense? Anybody?
Yeah.
What does h of 1 mean? It means z is equal to 1. What does z equal to 1 mean? Omega is equal to 0. What does omega equal to 0 mean? DC. And we are given that I want the DC gain to equal to a certain value. So again, h of 1 means h when z is equal to 1. Z equal to 1 means z equal e to j omega means omega equal to a 0. Omega equal to 0 means DC. Keep that in mind. I mean, we've seen it when we looked at the simpler filter. The gain of the filter at this frequency, I substitute z equal to 1. What is the gain of the filter when I am very high frequency? What did we substitute z? Negative 1. Z equal negative 1 means omega equal to a pi, which is the highest frequency. Is that clear? Everybody?
So you're saying that to solve for A, you just set Z equal to 1.
That's what we're going to do. So h of 1 is going to equal to 1 minus 1.90211 plus 1 divided by 1 minus a. And therefore, we can calculate the value of a, which is going to equal to 0.980422. Is that clear? How do we get the difference equation from this?
H equal YZ over XZ.
Anybody wants to read me the difference equation? Nobody wants to? We're going to write this as y of z divided by x of z. We're going to multiply across, and then we're going to take the inverse z transform. Make sense? What is that equation going to look like? It's going to look like 0.9804 multiplied by y of n minus 1 plus x of n plus 1 minus 1.902113 x of n plus x of n minus 1. Are we in agreement?
Can you go over the x's?
Yeah. So what is, if we let's do it on this side here. We're going to have z multiplied by y of z minus a multiplied by y of z equal to z squared multiplied by x of z minus 1.9 z multiplied by x plus x. And therefore, we're going to have y of n plus 1 minus a y of n equal to x of n plus 2 minus 1.9 x of n plus 1 plus x of n. I'm going to move the a multiplied by y of n to the other side. And then I'm going to shift everything by 1. So I'm going to get y of n equal to a multiplied by y of n minus 1 plus x of n plus 1 minus 1.9 x of n plus x of n minus 1. Make sense?
Yeah.
Okay. Now when somebody looks at this looks like a fine difference equation. What is the problem that we do not like about this equation? Is there anything we do not like? Is this equation describe a causal system or not causal system? Non-causal. How do you make this causal? What is it?
Make A 0.
Initial
No.
condition?
Sorry?
An initial condition?
No. Fort Walton? How do we make this system causal? It's okay. We'll say it, but I want you to remember it forever. What we can do is we can add another pole at the origin. So what happens? So this system is not causal. To make it causal, add add a pole at the origin. How does that work? So now we're going to have a system that looks like this. We have a pole at the origin, we have another pole here, and we have two zeros here. What is the transfer function h of z going to equal to? The numerator is not impacted. However, now I'm going to have z multiplied by z minus a, which is going to equal to z squared minus a multiplied by z. Make sense? Does everybody see it?
Yeah.
Why? When the numerator was higher than the denominator, the system is not causal. If they're the same order, then the system becomes causal. And you can do the same work we've done here, multiply across, you're going to see that y of n is going to depend on x of n and previous x of n's. Any questions? Is that clear? Everybody can remember that? Okay. What is the impact of adding this pole at the origin? Is it going to change the frequency response of my system? Yes or no? No.
No.
Why not?
It's at 0 and it's all equally distanced from the
Yes,
pole.
because the origin is at equal distance from all the frequencies. And that distance is equal to a 1. Make sense? So it's not going to impact anybody. The only thing it's going to do is going to shift the output, and in this case we shift it by 1. I could have put 2 poles here, shifted by 2. Okay. So let's run this filter.
So these are IIR filters.
Yeah. It's too early to be confused. Wait 2-3 weeks and you're going to be like, oh, just remind me where we are now. We are in the IIR filter. Okay. Go away. Okay, so this is our filter that we just designed. So here is our pole 0. This is the unit circle. 2 poles, 2 zeros. Here is the frequency response. It's going to remove the 60 hertz. And this is how the shape of the frequency response looks like. And this is what happens when we apply, when we have an input that is a 60 hertz sinusoidal signal. The output is 0. And what else we have? And this is the output when we input a sinusoidal signal that has a frequency that is 60 hertz. Now somebody's going to say, you said the same thing twice. And I did. This is the output when we apply the sinusoidal signal that is 60 hertz. This is the output when we apply the 60 hertz signal. I said the same twice, although I changed a word. But what is the difference between them? One using the filter command and one using a difference equation.
Yeah.
So I'm going to just take one of these screenshots and we'll go over the code in a second. Zoom is hijacking the screen.
So is there an initial condition for that?
I assume the initial conditions are 0.
Or 0? And so the filter function sets initial conditions to 0 by default,
Yeah,
right?
by default are 0. Okay, so this is our graphs for this example. And why do this and not, well, let's do it on the same page so when you read it, you can see them. And this is the code. So we have our numerator, we have our denominator, we're plotting the roots, and then we are using the freq to plot the frequency response. Same thing, we unnormalize, so multiply by the sampling frequency over 2 pi, the frequency response. And then we're calculating the output either using the filter command, which is filter, numerator, denominator, and the input, or using a loop where I'm going over the difference equation. Together? Is it okay to paste it here, or should you paste it the next page?
Next page.
Yeah, I don't know why we're trying to save pages. Okay, that's better. Any questions? Okay, let's do one more example. So everybody did not like the band stop filter. And everybody was suggesting, oh, why don't we just design a notch filter? So we're going to design a notch filter. Okay, so we're going to do it continued from the previous example. So the sampling frequency, we're going to assume is the same. So all the numbers that we calculated are the same for omega. What is our notch filter going to look like? Where are the advocates for the notch filter? How are we going to do the notch filter? That is going to remove the frequency that was pi over 10. We're going to place a pole and a 0 very close to each other. So we're going to have the 0 here. At what frequency? Pi over 10. So this is 1 e to j pi over 10. And we're going to place a 0. We're going to place a 0 at 1 e to j pi over 10. And we're going to place a pole at 0.99 e to j pi over 10. And therefore, we're going to have also one here. What does h of z look like? V minus 0.99 e to negative j pi over 10. And this is going to equal to k multiplied by z squared minus 1.9. This is the same numerator we had. And this is the new denominator, 1.8830 z plus 0.9801. This corresponds to 2a multiplied by cosine omega 1, and this corresponds to a squared. How do we find the value of k? Yeah, we want the DC gain to be equal to a 5. This will give me a k that is equal to 4.9505. Together? Okay, let's run this filter. Hide. Okay. So if you look at the filter, what do we notice?
Much better.
It looks like a notch filter.
Sharp.
This looks like a flag. But this is our input. And what is our output? It's removed. Okay.
So that's causal.
It is causal. Yeah. Because the order of the denominator is the same as the order of the numerator. However, I mean, you can see, as you've seen, we can always shift the output without affecting the frequency response of the filter. I can always add a 0 at the origin. What is the practical impact of adding a 0 at the origin?
0 or?
A pole at the origin. What is the practical impact?
Increases the order of the denominator.
Yes, it will increase the order, and therefore, when I implement the filter, I might need an extra storage and the delays, like all these things that I'm going to have to worry about.
So if you put a 0 at the origin, it would do what? It would knock everything out or let it,
Good question. Placing a 0 at the origin is not going to place a 0 or a pole at the origin will have no impact on the shape of the frequency response. Placing a pole is going to shift the output by 1. Placing a 0 is going to shift the input by 1. Make sense?
Yeah.
Any questions? Everybody familiar with basic designs of a pole 0 method? Placing the poles or looking at the pole 0 graph and being able to tell how this filter is going to look like when it is implemented?
Yeah.
Okay.
Hang on, how do you determine K again?
Same thing. We calculated, we want h of 1 to equal to a 1, a 5, and therefore we substituted 1 in z. We equated to a 5, and we found the value of k that will give me that. Okay. The next method we're going to look at in the design of the filter. So we are still where? What filter type? IIR. So the second approach is through continuous to discrete transformation. What does that mean? So what we're going to be doing is we're going to be designing a continuous filter, and then we're going to transform it to a discrete filter. Straightforward? Now somebody is going to ask, why are we designing a continuous filter?
Because that's the equivalent that we see in continuous.
That is, yes, and also because we have lots of tools and continuous time filters are well understood and designed and researched, and therefore we can use all the tools that help me design a continuous filter, and then I can just transform it to a discrete filter. Okay. Now it's very important for everybody to understand that, because hopefully not, but you might be confused in a few lectures like, oh, I thought this was digital signal processing. Why are we designing a Chippy-Chef continuous time filter? How is this related to what we're doing? You're going to find yourself lost. And that's why I'm doing this map here. So what we're going to do is the following. We're going to review Butterworth filter. Anybody heard of Butterworth filter?
I don't think so.
We're going to review Chippy-Chef filter. Anybody heard of Chippy-Chef filter? We're going to review Chippy-Chef type 1, type 2, and we're going to review elliptical filter. And we're going to mention Bessel filter. So what we're going to be doing next is we're going to do a review. So this is going to feel like an excursion of what we're trying to do. Make sense? We're going to need this review. Then, after we do that, we're going to be designing a continuous time filter. We're going to bring it back to being a discrete time filter. How are we going to do that? We're going to use different techniques to convert the continuous time filter to a discrete time filter. And these techniques are impulse invariance, so this is one technique. The second technique is bilinear transformation. And the third technique is the matched Z transform. Together? Is that clear what we're going to be doing? So the first part, we're going to review these filters. We're going to be designing continuous time filter. But then after we design the filter, we're going to look at different techniques of taking the continuous time filter and convert it to a discrete time filter. Okay, so with that, we're going to start with the first of these filters, which is the Butterworth filter. If I ask you with one word to describe the Butterworth filter, what would you say?
Smooth.
Excellent. Smooth. That was a smooth answer. If I have an nth order Butterworth filter, and this filter has a cutoff frequency omega cutoff, then it will have a frequency response that is given by h continuous of j omega equal to 1 divided by 1 plus omega over omega c to the power of 2 multiplied by n, and this is square root. This is the frequency response of the Butterworth low-pass filter. And if I want to plot the frequency response, the frequency response will look something like this. Of the filter. If I look at this filter, and this is n equal to 5, when I have negative 3 dB, what does that correspond to? The cutoff frequency. And then if I look at the slope of the stop band for the transition region, the slope is equal to negative 20 multiplied by n dB per decade. So this is the body plots of the filter, and this is in dB. The filter, if I were to plot the magnitude, it's going to look something like this. So this is my cutoff, this is a 1, and this is 0.7 or 7. So this is HC of j omega magnitude. Sounds good? So we'll look next class at the characteristics of the Butterworth and then the Chebyshev and the other filters, and later on we're going to take these filters and convert them to a discrete time. Any questions? Okay, we'll stop here.